let's take stock of what we've done. Some magic apparently has been performed here, and let's try to demystify it. This ensemble of ideas, as I've told you, is called the Monte Carlo method because of its chance-driven overtones. And there are some immediate, obvious positive points for it, some pros for the method. What are the various pros? First, a relatively small sample of points in the cube will give rise to accurate estimates of the underlying integral of a function. So, 1,000,000 points give us an error of no more than 1% with a confidence of 99%. But something remarkable has also happened. Nowhere in our estimates does the dimensionality d appear. In fact, the sample size estimate needed for our Monte Carlo sum does in no whit depend upon the underlying dimensionality of the problem. 1,000,000 points will give you an estimate with a 1% error. So will 1,000,000 points in 200 dimensions, or 1,000 dimensions, or 100 million dimensions. This is beautiful. And if the listener thinks back, she will say, we saw something like this. This is exactly what we saw in the context of polls. Of course, doing polls to estimate population sentiment seems on the surface very different from computing a numerical integral, does it not? But the underlying chance mechanism by which we approach the problem is exactly the same. And just as polls don't depend upon the size of the underlying population, so too the Monte Carlo methods don't care about the underlying dimensionality of the problem. These are wonderful attributes for an approach to computation, especially in what appear to be a completely intractable setting. But there are some caveats. So here are some cons of the method. First, the method very quickly gives rise to good estimates of j, the integral. But the method falters and breaks down if the error tolerance you need is exceedingly tight. If you tell me, I want an answer which is within 1/1,000,000th of a part of j, then you're going to need to sample something like 10 to the power 14 times. Oh, the number is getting large now. Now we're getting to be a significant burden. And if you want an even tighter tolerance, things blow up on us. Because the scaling is like 1 over epsilon squared. And the smaller epsilon gets, the faster that blows up. So, the method is very good at getting you a quick and dirty answer, maybe even better than dirty, a quick and reasonably accurate answer. That is going to break if you demand exceedingly tight precisions. Again, you might be reminded of the same kind of phenomenon we encountered in polls. If you're looking at polls and you're looking at a political setting and we want to try to separate two candidates, if they are very close to each other, polls start breaking down. And this is exactly the same phenomenon. Now, the listener might have another objection. And she might say, look, this is okay, but if you're going to tell me I can't get smaller than 1% error without things breaking on me, but I need more, I need better precision, what can I do? Well, the short answer to that is, life happens. Okay, we can't always get everything we want. But let me borrow or paraphrase a bromide of T.W. Kerner from Oxford, who pointed out that in any case, a principled and reasonable answer in a small number of steps is to be preferred to no answer at all in an infinite number of steps. With 1,000,000 steps, I get an answer with an error of no more than 1% and a confidence of 99%. That's surely better than no answer at all in trying to compute a sum over 10 to the power 95 terms. That's hopeless. Right? So, here's a practical reason why this at least gives us a way forward. It gives us principled answers. There is another con, however, and that is this computational method is intrinsically chance-driven. If I do a Monte Carlo computation today, I sample 1,000,000 points, add them up, divide by 1,000,000 and say, here's your answer. And if I do this computation tomorrow, I'm going to get different answers. This is troubling. Something deep and fundamental has changed. And to put this in context, bear in mind that computation through the middle part of the 20th century historically meant two things. When we computed precisely and we computed certainly. Computation connoted precision and certainty. 2 plus 2 was always 4 and will always remain 4. Now, this was the idea of computation from prehistory all the way through the middle of the 20th century. With the advent of these probabilistic methods, philosophically, something fundamental had changed. Computation using these methods now connoted both approximation, we are giving up getting exact answers, and it connoted also a lack of certainty. It's not only that I'm getting an approximate answer, in fact, any numerical integration is going to give you an approximate answer. But even worse, there's a possibility that my answer is completely and totally and irretrievably wrong. But we take some comfort in the following understanding. If 100 people do this Monte Carlo simulation, on average, 99 of them are going to get good answers within 1% of the true answer. One of them, sadly, on average, is going to be out in left field. And very sadly, he won't know that his answer is wrong. There's no way of knowing a priori that your sample was aberrant. But that's life in the 20th and 21st centuries. Right? Following Kerner's bromide once more, keep in mind that in any case, a principled answer in a small number of steps, with some probabilistic guarantees, is always better than no answer at all in an infinite number of steps. Following its discovery in the 1950s, the Monte Carlo method has taken over the computational landscape. Now it's a common garden tool in the hands of professional scientists in all kinds of areas. Climate change engineers use it to do climate modeling. So do engineers of all stripes in fluid mechanics, in electromagnetism. Physicists use it, chemists use it, biologists use it, mathematicians use it, sociologists use it. An auditor who has to check the transactions of a large company over the course of a year faces a large number of files of transactions. How does he handle a very large number in a short period of time? He samples randomly. Again, we're using Monte Carlo methods. These tools now are embedded in all our common computational devices, in our mobile phones, in our computers, over the internet. The Monte Carlo method has become ubiquitous. At its heart, all we're doing is the same phenomenon that we're appealing to, that worked for polls. The engine fueling the Monte Carlo method is this wonderful, magical law of large numbers. Now, I could go on to give you more beguiling examples, but we shouldn't be greedy. So, we're going to stop with our applications at this point, conclude the segment, and we'll come back when we finish up with all the required lectures with some optional dessert items where you'll see some more, hopefully intriguing, beautiful examples.